Next talk is by Ariel Zhitnitsky, Vacuum Energy of the Universe, Large-Scale Magnetic Field, and Non-Trivial Topology and Quantum Field Theory. Okay.
Okay, thank you very much. It's honor to speak here. And let me say that this talk is mostly based on two recent papers with Andrei and myself. And essentially ideas came when we walk along this beach in UBC area, but we never went to the actually wrecked beach, so for some of you who knows what it is. Okay, so essentially, let me start. So, but I start with some kind of preliminary remarks. So what is the energy? Because normally when people discuss energy, it is just people assume what is the energy. Nevertheless, I want to say something about energy in quantum field theory, and young generation probably never studied this in quantum field theory courses, and that's exactly the reason for my preliminary remarks here. So this energy has non-dispersive nature. It is not expressed in terms of the conventional scattering amplitude, because normally when people discuss so-called Fock theorem, which says that all S matrix essentially contains entire information for physical observables. So, and for all generation, we definitely know it is not quite correct. So all these novel effects are due to some kind of non-trivial topological sectors in gauge systems, tunneling transitions between them. And the effects I am talking about here in this talk are non-local in nature, cannot be expressed in terms of local curvature, in gradient expansion, in terms of non-local characteristics of the system. And we discuss the holonomy. So the plan of my talk is the following. First, I want to apply all these ideas, which can be tested in a simple quantum field theories, to the dark energy and inflation model. So essentially, the computations have been done in some simplified model, so-called deformed QCD, in hyperbolic space. I did these computations. But I want to actually discuss real physical systems related to the inflationary and dark energy. And I also want to discuss a little bit about magnetic field, because essentially it is a link, it is not a separate question. Okay, now, formulation, what is the energy and what I'm talking about of non-dispersive energy, what is it? The simplest way to explain that in terms of so-called topological susceptibility, because essentially vacuum energy can be understood in terms of, because it is a second derivative. So avoid to confusion and all future questions, please. It is a weak T product. It is not Dyson T product, okay? So essentially, again, young generations probably never study the difference, but nevertheless, it is a weak T product. So the point is the following, that this correlation function does not vanish. And it is a total derivative. It does not vanish. Because it is a weak T product, not Dyson T product. More than that, it is known that this so-called topological susceptibility has a wrong sign. What does it mean, wrong sign? It is not what corresponds to S matrix elements, okay? And it has a Pauling momentum space. You would say, oh, it is a massless degree of freedom. No, it is not. It is a massless degrees of freedom, which Veneziani introduced, so-called Veneziana ghost. But nevertheless, it is a not physical propagating massless degree of freedom, okay? So let me explain in terms of S matrix elements, which is actually related to the Dyson T product, not weak T product. When we are talking about Dyson T product, in Euclidean space, it is always sign minus. So this topological susceptibility in Euclidean space-time would be negative. Nevertheless, to resolve our QCD problem, well-known U1 problem, you must have a positive sign. And conventional terms, again, in terms of S matrix, if you have a gap, you have always negative, exponential negative, such that you have at large distances, you do not have sensitivity. So essentially what happens in the late 70s, Wheaton simply postulated this term, and Veneziana did something more. He actually postulated so-called Veneziana ghost to saturate this wrong sign in topological susceptibility. So that's my preliminary, and in some models, this non-dispersive term with the wrong sign can be explicitly computed, and I'll show that. And it is precisely due to the topological sectors in gauge theories. Okay, so these contributions in principle cannot be described in terms of conventional degrees of freedom, wrong sign. They're inherent non-local in nature and formulated in terms of non-local large gauge transformations, in terms of holonomy. And these terms may exhibit long-range features even if you have a gap similar to the QCD gap, okay? And all these effects which I mentioned for topological susceptibility actually share with a vacuum energy, because there is a absolutely precise relation between the two. Now, let me show something from the latest QCD. So conventional physical degrees of freedom always contribute with this sign minus, and just something what we know. But definitely we have a sign plus. It is some kind of delta function. It is so-called contact term. So I'm talking about not simply some kind of academic questions. It is something for real. It is a part of our nature. Okay, now I come back to the cosmology. So I gave this preliminary just to explain that the energy I'm talking about, it is not something you can express in terms of local degrees of freedom like inflaton or whatever. It is not. Okay, so this essentially proposal, it is a synthesis of two previously naively unrelated ideas. So the first idea, it's quite old idea, with just due to Andrei, with many other people as well. So there is some kind of extra S1, and important part of S1 for Andrei was it is just thermal as the initial state, and he discussed different instantons with essentially some kind of generalization of Hartle-Hawking instantons. Inflation starts as when you have a nucleation of the system. And once you have a nucleation, you go to the Lorentz space. Okay, so essentially that's from his papers. And essentially the difference is between R1 and S1 here. It's exactly what Andrei discussed long ago. So for him, S1 was extremely important because this is a way how he formulated initial conditions. Torus, which actually Andrei discussed here. Now, the nucleation start in this approach. It just you go to Lorentz in space-time because you go from from Euclidean to Minkowski. You just do conventional analytical continuation, and after that you have exactly this exponential behavior. Okay, now. Completely unrelated idea, which again I discussed before, Andrei, and as I said, we combine this idea together while we are walking along the beach at UBC area when he visited UBC a number of times. So now S1 in my part of the story is very different. So let's assume for a second that we have some kind of gauge theory. I call this QCD bar. So assume it is just like QCD we know and love, but with a different scale. So it is not Planckian scale, it's a little bit less. And when I discuss dark energy, it will be a real QCD we know and love. So essentially important part here, it's non-trivial value for the holonomy. When you compute exactly this integral, and S1 is important because you take the integral along dx4 here. And in our framework, the vacuum energy entering the Friedmann equation is defined, and let me repeat, it is a definition as a difference between the energy computed in the non-trivial background and the energy computed in trivial space-time. So the point is the following, that this difference is expressed in terms of the length of this S1, okay? And this subtraction prediction is consistent with the conventional subtraction of all UV divergences. It is non-local function of the geometry because this length enters precisely in this definition and cannot be removed by any UV contour terms. So it is an infrared nature. So where does it come from, this prescription? Again, I cannot prove, I cannot disprove this prescription, but nevertheless, it is a part of the story. So it comes from the very old paper by Zhitnitsky. And of course, nobody noticed this paper until the much later times. So, and many people discuss precisely what is the right-hand side of the Friedman equations, and in different fields of physics. Bjorken discussed that, and when he was actually in my office, we discussed for many, many hours the way how actually Bjorken understands this part of the Zhitnitsky paper. Ralph, he also visited UBC. I also actually knew from him. He even actually mentioned my name in his paper, 2002 paper, but I didn't take this paper seriously. And Bill was staying in my office together with Ralph. Again, I didn't get it right. And only Grisha Lovic in 2008 actually explained me in great details what is a great idea is. So again, for many, many hours, we discussed this idea with Grisha, and I took it seriously by attending many, many workshops which Grisha organized, cosmology in laboratory, okay? So that's the way how I know about this idea. So now come back to the holonomy and linear correction. So what is important part here, that normally when people discuss local quantum field theory, that they say that the physics must be actually proportional to the local curvature. And if you have some kind of parameter, let's say kappa, in this case, it must be kappa square because it is a curvature. Let's consider specifically hyperbolic space, because that's the way how local curvature looks like, okay? So what I want to discuss, I want to say that it is actually linear part as well. And I did specific computations here. So we want to test this idea about the linear portion in gauge series with non-trivial holonomy. As I said, S1 is a non-trivial part. And in this case, the claim is that the correction, absolutely physical, gauge invariant correction, they come as actually linear in kappa. And these computations in simple model can be explicitly performed, and you see that that's indeed a linear part, okay? As I said, the definition for the vacuum energy, it is a not Dyson, it is a weak T product. Okay, so the computations are based so-called colorons, and it is some kind of topological objects which interpolate between different vacuum states, topologically distinct, but physically identical. And normally all these non-trivial holonomy configurations contribute zero contribution. Nevertheless, essentially, and they are very, very different from conventional instantons because instantons have a trivial holonomy, okay? So, but nevertheless, it turns out when you do in a grand canonical ensemble, in this case, it is a finite actually. How you can view such kind of configurations? This configuration could be thought as some kind of n different species of monopoles which carry fractional topological charge. But nevertheless, the total charge is definitely integer, as supposed to be. And confinement can be also understood in this picture. Now we believe actually in QCD confinement is due to such kind of colorons, Pierre van Balk colorons. Okay, so let me explain only one crucial element. Where is the difference? Where does it come from in between these two cases when you compute on R cubic and hyperbolic space? So when you do computations on R-cubic space, in this case, definitely we know the monopoles, we know that the cutoff scale, it is a, roughly speaking, Higgs. So that's exactly where cutoff happens. When you have a hyperbolic space, the cutoff happens at a different scale, and monopole is characterized by a different function. So essentially, once you take into account all these differences, it turns out that the vacuum energy, again, it is a weak T product, vacuum energy. It's definitely indeed proportional to first power because the fugacities are different, okay? So that's exactly the point. When you, after that, compute the pressure, when you compute the rho, it turns out that the corrections here are linear 1 over tau, and they're both exactly the same. So, as I said, if I take precisely the prescription we discussed before, that the right-hand side is defined in terms of the difference between the computations on non-trivial background and trivial one, in both cases, it is the linear part, and it is a like constant, but of course it is a not. So delta P, delta rho, it is -1, as it would be cosmological constant, but of course it is not cosmological constant. It is something different. It is something what you compute as a difference. So, and all other parameters can be computed in terms of P and rho. So the claim is the following, that this de Sitter behavior, it is a not local dynamical degree of freedom. And inflation cannot be formulated in terms of local degrees of freedom. So it should be thought this energy as a Casimir type energy generated by the tunneling transitions, not like a dynamical field. So now the just physical question, how a system with a gap could be ever sensitive to arbitrarily large distances? Because it's some kind of looks like nonsense. Because if you have a gap, you would expect such kind of exponential suppression, exponential behavior. Now, let me explain in a simple way. So let's consider so-called Aronoff-Kaffer effect. It's not Bohm-Aronoff effect, it's Aronoff-Kaffer effect. So what is it? It's just you have a superconductor, you put a charge inside of this superconductor, and you have a magnetic solenoid, and you're moving in this superconductor. And you would say, oh, you have actually definitely screening because the charge inside must be screened. So everything must be exponential. But at the same time, you definitely know that physics does depend on this charge on arbitrarily large distances. So there is a long range order. Definitely there is a -r here, exponential behavior. So Aronoff and Kaffer in their paper, they call this so-called modular operator. So in our language, people who study gauge theories, we call this not modular operator, but large gauge transformation operator. But it is exactly the same. It is the same operator if you look at their paper. And look at our paper, we see analogy, precise. So that's exactly the reason why system with a gap has actually sensitivity to arbitrarily large distances, because it is a not propagating degree of freedom. Okay, now about the inflation. Go back to inflation and how inflation actually ends. So in a simplified version, when there is no any standard model particles, no any other gauge fields, in this case, it would be the end of the story. It is a final destination. So it is exponential expansion, and that's it. However, we do have interaction with a standard model particle. Okay, so and now I want to discuss what is going to happen here. So in principle, the computations are well defined. We definitely know how to do it. It is a very different from infinitely many model, which Andrei Linde discussed just in the previous talk. It is just unique, it is a well-defined. Unfortunately, computations are profoundly complicated. So, but nevertheless, procedure is perfectly defined. So one should describe the relevant Euclidean configuration satisfying proper boundary conditions, similar to Caloron I discussed before with the non-trivial holonomy. One should compute the corresponding path integral and accounting for the tunneling transitions. Now we have to do it together with actually all gauge degrees of freedom related, which is a standard model particles. And after that, we should compute rho, we should compute p, we have to actually derive delta p, delta rho, and after that, we have to derive omega delta p, delta rho. It would be deviation from -1. So all the steps are perfectly well defined, but it just, you know, there is no way I can perform such computations because even the simplest Euclidean configuration which satisfy boundary conditions de Sitter space is not known yet. So there is some kind of analogy with the dynamical Casimir effect when photons actually radiated not from the conventional virtual particle fluctuations, but the photons come from the configurations which describe the tunneling processes. But otherwise, it is very similar to the dynamical Casimir effect. There is a difference here that actually photons comes from the configuration describing the vacuum tunneling processes. Okay, so again, it is a hard technical problem in a what sense? Because latest people, and I do computations in Euclidean space-time, but when you're talking about emission, definitely it's in a Minkowski process. It's hard. Okay, fortunately, some kind of key elements can be understood in some simplified models without all these complicated computations, which I mentioned before, step 1, 2, 3, 4. It is very similar to Veneziana ghost, essentially, and in a sense, it is very similar. So, and the end of inflation, and it can be, by the way, it can be explicitly derived, this Lagrangian. I derived it in a simplified model that it just is given by triangle anomaly. So, but B here, it is not real physical field. It is not like axion. You look at this Lagrangian and you say, oh, but that's exactly like axion field. No, it is not, because the axion, it is a real dynamical field, okay? And there is not canonical kinetic term for B field. It is a topological non-propagating field. So the way how you introduce into the system, it is a Lagrange multiplier. And after that, you keep track on this Lagrange multiplier. So it enters the effective Lagrangian in this way. So in some solvable model, I can do that, and I did that. So you see that actually effective Lagrangian can be derived. By the way, in condensed matter system, this technique is so well known that essentially instead of summation, our topological sectors, it is actually replaced by auxiliary non-propagating fields. And the topologically ordered system, this technique is very well known. So I don't want to discuss this technique here, but I have a paper on that. Okay. Now, in QCD context, this B field, which is an effective field, auxiliary field, actually has some kind of physical meaning. B dot, it is a so-called chiral chemical potential. Again, in QCD, such kind of effective Lagrangian has been discussed many times long ago, and there is so-called chiral magnetic effect in QCD. And by the way, we wrote a paper with Dima Kharzeev to observe this chiral magnetic effect, and in Brookhaven, and after that at LHC, it has been indeed observed. I believe so. So, but for now, the point is the following, that again, mu5 here in the QCD context, it is again, it is a not real physical propagating field. There is no kinetic term for that. it is indeed auxiliary field. Okay, so physical meaning mu5, it's similar to actually Hubble parameter, which discuss the difference between. Now, there is a helical instability. Again, it is a well-known. So if you go to this Lagrangian, people discuss this Lagrangian many times. And if expectation value B dot is non-zero, it's known it's unstable. So, and this instability, so-called helical instability, describes what's happening with the chiral chemical potential in heavy ion collisions. Here, essentially, it tells you something more. It tells you that this energy related to mu5, it is distributed, it is transmitted to different particles, standard model particles. And what is the typical time instability? It is alpha -2. So for example, coming back to cosmology, if alpha for electroweak, for electromagnetic, and for strong, alpha is something like 0.1. So it's about 100. I cannot compute with accuracy better than that, but essentially my view on a number of E-faults is essentially, it is expressed in terms of coupling constant we know and love. It's alpha. Okay, so the deviation from de Sitter, now it's related to this small coupling constant alpha. Again, it is not related to some kind of potential expressed in terms of the local field. Now, exactly the same idea applied to the dark energy. So what is the lessons from what I said previously? There is a new, fundamentally new type of vacuum energy, which cannot be expressed in terms of the scattering amplitude. It's not expressed in terms of S-matrix elements. Lesson 2, it emerges as a result of tunneling between different degenerate topological sectors. It has a non-topological, non-dispersive, non-dispersive origin related to the non-trivial holonomy. Lesson 3, and we identify this new type of energy with a cosmological vacuum energy. As I said, we have to subtract the same computations computed on R4 before I say what is the energy is. Now, instead of unknown gauge theory, which I mentioned, I conjecture for inflation, I'm talking about real QCD with a lambda QCD I know, with the quarks, with the gauge fields, with the gluons I know and love. And in this case, I can apply all the formula I discussed before for my specific QCD. Now, the point is the following, that in this case, this parameter related to the just S1, again, you compute what is the Hubble, what is the dark energy, and it turns out that all numbers are about correct. As I said, it's very hard to compute. It is a real QCD. It is a strongly coupled regime. And even lattice people cannot do the computations. But the crucial part, it is a proportional to the linear part, not quadratic, because it is not just curvature, which enters the physics, which I explained before. Okay, so now, definitely, in this case, there is interaction with the standard model particles in the case of dark energy. But now there is only one massless particle on this scale. There is a massless particle, it is just photon, because all other gauge fields are definitely heavy. So what does it mean? It means that we did discuss reheating in terms of inflation. Now we are talking about actually what's happening with the dark energy, how this energy transforms to the gauge field series, to the photons. And in this case, we are talking about large-scale magnetic field. So as I said, people have been talking about large-scale magnetic field for years. It is a very, very interesting question. It's a very hard question, and there are so infinitely many papers on that. So we are advocating actually unorthodox mechanism, which is dramatically different from every paper which is written previously. So we are talking about that the B field is generated on enormous scale from the very start, similar to reheating in inflation studies, which I discussed before. And there is no need for any amplifications of the scales because it is characterized by the largest possible scale at the moment of formation. And B field is correlated on enormous scale, gigaparsec scale, from the start. What is the origin of such correlations? Well, let me show something from Neronov paper. So now we know that actually B field must exist. And right now it is from 10 to minus 9 to 10 to minus 15 Gauss. And this field must be correlated on enormous scale. It is actually gigaparsec scale. This is already gigaparsec. That's already 10 gigaparsec scale. So we know that such kind of magnetic field exists. So how you can arrange magnetic field correlated on so huge scales? So that's the answer, the way how I am suggesting to answer this question. So again, the same effective Lagrangian we discussed before. And again, it is something what we discussed before in terms of inflation, but now mu5, it's B dot for the QCD scale. Again, this equation has been discussed many, many times in terms of the axion physics, in terms of the generation of a magnetic field. But the difference is it is a not real dynamical degree of freedom. It is an auxiliary Lagrange multiplier here. Okay, so it is just, there is no kinetic canonical term here. And that's reminding that B field was introduced as a Lagrange multiplier. So it is known that the equation tells you that there is a helical instability, no doubt about that. People discuss that. So, and B field will be generated, and this exponential behavior again is known. It is a similar to reheating I discussed for the inflation. And we definitely know that the large wavelengths are unstable with respect to emission. So that's very, very similar to reheating, but now it is actually generation of the magnetic field. So if you put numbers in, it's about something like 10 to minus 10 Gauss. It is definitely consistent with this window, but essentially I'm not claiming that I derive this number because, as you can see, there are so huge uncertainty in every single step, but nevertheless it just goes this way. So I am about to conclude. So essentially conclusion for inflation, that there is a linear correction which is a very different from the local conventional effective Lagrangian approach where you have only quadratic h square. So, and this linear correction can be explicitly derived, can be explicitly computed in a simplified model when you have S1, and it is clear why. This is similar to Aronoff-Kasher effect, where dependence on the A field and not F minu field. And if you apply this idea to inflation, that in this case, the reheating related to actually coupling constant alpha square. So essentially it is alpha minus 2. It's about 100 at this scale. I cannot compute better than that, but nevertheless, it is about right. And it is a non-local in nature phenomena. So just there is no way I can describe this phenomenon in terms of effective field. Okay, and application to the dark energy and B field, again, very similar in the sense that I can estimate what is the dark energy density. In terms of the lambda QCD, we know for sure. And we can estimate the Hubble scale. This is the only dimensional parameter we have on the problem. And it is about correct, 10 to minus 3 eV. And when essentially all energy which we have right now, dark energy, will be eventually transferred to the magnetic energy, well, you have to wait 100 times Hubble years, okay? So, and magnetic field, it's about 10 to minus 10. So I don't know. I don't have time to discuss something else. So I better just stop here. Is it correct, or I have a few more minutes, Valera?
You have -4 minutes.
Oh, okay. So I stop better here. So, but in case if you want to know about physical meaning, I have few extra slides. I stop here.
Okay.
Thank you.
Thank you, Ariel, for your interesting talk. So now we have some time for questions. Alexander Wickman, please.
Hi, Ariel. Nice to see you. Very interesting
Nice to see
talk. Unfortunately, I missed to read your very interesting papers on this stuff before. But, you know, I just have a comment which you may find very trivial, maybe not. So if you look at the structure of the Lagrange multiplier applied to this FF dual, then there is one curious fact that if you neglect a kinetic term for your gauge field, by, let's say, using very heuristic arguments like, oh, this gauge field is anyway confined, because it's confined, it should not propagate. If it doesn't propagate, there is no kinetic term, something like that. Then actually you would recover unimodular gravity. Moreover, what is very funny is that would be very similar to the construction by Knott-Appelboim, and then this B in kind of first order theory would be the momentum for the basically for the whole, if you want, for the whole space-time volume between different hypersurfaces. So it's completely non-local, but it kind of makes sense, because if you have this QCD confined vacuum everywhere, it's a global properties, and you can say something like that. So it's kind of, it's very close to what people call unimodular gravity in reality, but only if you neglect, of course, kinetic term for your gauge field.
Yeah, I agree with this comment. So essentially, all papers which I know, they introduce kinetic term, and when they discuss kinetic term, okay, whatever they find, they find. But essentially, I derive this effective Lagrangian, and I definitely do not see the kinetic term. There is no degree of freedom, propagating degree of freedom, and it is definitely non-local phenomena. So I absolutely agree with this, with your comment, and I didn't know that there is actually some kind of discussions of similarity, what you mentioned now. Thank you.
Yeah. It's kind of, you see, it would be very elegant, because in that sense, this FF dual term would provide what David Finkelstein used to call, like, I don't know, 60 years ago, a fundamental volume element coming from atomic or whatever nuclear physics. Okay, in some sense, that's could be interesting discussion.
Very interesting. Okay, I wish I knew about that when we actually visited Jerusalem together, and we walked there and we could discuss that. Okay, now I hope sometimes we meet and we just walk in Jerusalem and discuss that.
Well, not only in Jerusalem. It's a kind of unique city, but it's not the only one.
But we walked together in Jerusalem. That's I remember.
True. That's true. That's true. Thanks.
Okay, more questions? I cannot see more questions.
Okay, very good.
Thank you,
Okay.
Ariel. Thank you, Andrei, for your talk. Thanks everybody for attending this session. So this evening session is over. I hope to see you tomorrow morning, Moscow time. Yeah. Bye.